Okay, so in last class, we solved all these problems, okay? So in the exam, we may set this sort of problems. Like in this case, you are asked to, number 6, you are asked to calculate the center to center distance between the closest atom, okay? Center to center distance. That means you are asked to calculate nearest neighbor distance, NN distance, nah? Nearest neighbor, which is basically 2R. How will you calculate R? Like it is BCC. So at first you will calculate A from A. For BCC, A is actually A equal to 4R divided by root over 3. From this relationship, we can calculate R. And then what is the edge dimension? Edge dimension is the unit cell length A. That means for this problem, at first you will calculate B, and from B you will find out the answer A. So that's the one. Okay. So in these problems, we have calculated overall density of the material. Overall density of the material, rho. Okay. Sometimes you see linear density is very important. Now, what is linear density of atom? Linear density of atom is defined as, suppose this is one unit cell. What is this unit cell? What type of what is the crystalline nature for these materials? This is FCC. Okay, face centered cubic. So for this one, if I draw a line, this line, okay, so this is one-dimensional case. One line I am drawing here. So in the, what is the length of this line? If this is face centered cubic, this distance is A. This distance is also A. So that is Pythagoras. So that distance will be root 2 A.
Right.
And then you will calculate how many atoms are there in this line. How many atoms are there? So it is one-dimensional case. So half of the atoms are here along this line, half, and other half is, if you extend the line backward or forward, so other half will be in the other unit cell. And then this corner is also half, and the middle atom fully lies along this line. So number of atom along this line will be half plus 1 plus again half. So number of atom will be 2 in this case. So linear density of atom is defined as the number of atoms divided by the unit length of direction vector. Later on, we're going to study when we indicate this one. This is called the crystal direction as well, which we are going to study later on. Okay, so you don't need to worry about this thing. So what will you do? You will find out the length of the line and how many atoms are situated along that line. You will calculate. So number of atoms divided by the unit length is called linear density of atom. So in this case, length is root 2A. A is given, so it's root 2A, and number of atoms is 2. So it will be 3.5 per nanometer. So that's the linear density of atom. So instead of along that line, if I ask you to calculate linear density of atom along the edge dimension, like this one, can you see this one? So what is the length of this line? This length of the line is A. Okay, and how many atoms are there? Half plus half, so 1. This is linear density will be basically 1 by A. Okay. Now, if I ask you to calculate linear density along the body diagonal, do you know what is the body diagonal? Body diagonal is the longest diagonal. And what is the length of the longest diagonal? Length of the longest diagonal is, it will go through the middle. So length is root over 3A. And how many atoms are there? It is face-centered cubic. So no, only this corner atom will lie along that line, this corner atom along that line. And through the body-centered position, actually no atoms are. The line will not pass through the diameter or radius. Okay, so it will pass just only the side. So along the body diagonal, half atom here and half atom there. So 1. It will be basically along the body diagonal, it will be linear density will be 1 by root over 3a. Now, instead of for this along that direction, instead of face centered cubic, if it is BCC, body centered for BCC, if it is BCC, along that line, actually it is root 2a. And how many atoms are there? Because this atom will not be there. The body center atom is there. So it will be actually 1. 1 by, for BCC, linear density along the face diagonal is 1 by root 2a. And for BCC, linear density along the edge dimension is same as before. It is 1 by a. But for the body diagonal, now half atom is here, half atom is there, and the body centered atom fully lies along that line. So it will be 2 by root over 3a. So similarly, I may ask you to calculate linear density of atom in various crystal directions or various along various lines. Okay, so I hope you will be able to solve it.
Sir.
Okay, I'll take question later on. So write it down. At the end of the class, I'll reply the question. Okay, now the density of packing or packing factor. You have seen previously number of atom per unit cell. We have calculated number of atom per unit cell. That number is n. We denote that number by small n, and the value of n is n equal to 1 for simple cubic, n equal to 2 for body centered cubic, and n equal to 4 for face centered cubic. Remember that one. And also we have seen that r equal to a by 2 in case of simple cubic, and r equal to root 3 a by 4 in case of body centered cubic, and r equal to root 2 a by 4 in case of face centered cubic. Now you see, if you look at the three-dimensional view of the three-dimensional view of this unit cell, then you'll see in case of simple cubic crystal, in a unit cell, most of the unit cell will remain empty, and then for body centered cubic, the empty place will be less, and for face centered cubic, it will be more or less. Actually, that measure is called the packing factor. So packing factor is actually defined as the fraction of the volume occupied by the spherical atom. We consider the atoms are spherical in shape compared to the total volume in the structure. So packing factor is denoted by PF, and it is defined by volume occupied by the atom divided by the available volume in the crystal structure. Now, what is the available volume in the crystal structure? That is the volume of the unit cell, BC. And volume occupied by the atom will be N is the number of atom in a unit cell multiplied by volume of an atom. So atoms are in spherical in shape. So volume of an atom will be 4 by 3 pi r cube, and then N is the number of atom available volume in the structure. Okay. Now, if it is cubic crystal, so available volume in the crystal structure will be a cube. It will be a cube. Okay. So N into 4 by 3 pi r cube, and then now if I ask you to calculate packing factor for simple cubic crystal, in case of simple cubic crystal, packing factor in case of simple cubic crystal is at the denominator it will be a cube, and then what is the value of N in case of simple cubic? It will be 1 multiplied by 4 by 3 pi and then R cube is there. R is simple cubic. So R will be basically A by 2 and then cube. Okay, so if you simplify that one, that will be A cube will consider that will be basically pi by 6. And if you substitute the value of pi, actually this will give you 0.52. If you express it in percentage, it will be 52%. Now, what is the physical significance of this one? So we just calculate a packing factor for simple cubic crystal, and we have seen that packing factor for simple cubic crystal structure is 52%. That means in a simple cubic unit cell, whatever the volume you have in a unit cell, among it, only 52% is filled by the atom, and the remaining 48% is empty. And this 48% is called actually interatomic space, which you have studied in your school level science book, interatomic space. So in case of simple cubic crystal, interatomic space is 48%. Okay. So in this, we have calculated packing factor for this one, 52%. And if I ask you to calculate packing factor for BCC crystal, same formula, the value of n will be, in this case, value of n will be 2, and then 4 by 3 pi r cube. Okay, and r is actually root 3 r by 4. So, and if you calculate that one, it will be 68. If you express it in percentage, it will be 68%. What is the interatomic space in this case? Interatomic space in this case is 100 minus 68. So it will be 32%. If we do the same thing for FCC crystal, n equal to 4 and r equal to root 2 by 4. If we substitute these values, it will be root 2 pi by 6, which is 0.74. Or if you express it in percentage, it will be 74%. That means whatever the volume you have, among it, 74% is filled by the 74% is filled by the atom, and remaining. So in this case, IAS means interatomic space will be 26%. Okay. So now you see, this is actually one of the closest packed crystal structure. And we have another closest crystal structure which we are going to study later, which is called hexagonal crystal structure. And hexagonal is called hexagonal closed packed crystal structure, HCP, hexagonal closed packed crystal structure, which we will study later on. Okay, so in your syllabus, it is mentioned two special crystal structure. One is sodium chloride crystal structure, another is cesium chloride crystal structure. So at first, we are going to study sodium chloride crystal structure. That's very important one. Just if you look at the stack of the atom in a unit cell, so that will be the 3D view of a sodium chloride crystal structure. So this one is chlorine, and the smaller one is sodium, and then again chlorine. Okay. Now, what is the crystal structure? If you look at, so obviously, it has got two sublattice. One is chlorine lattice, another is sodium lattice. If you look at the chlorine sublattice, look at here. So chlorines are located at the corner and also the face center position. Chlorines are located at the corners and face center position. Okay. So okay. If I ask you to draw a typical unit cell, answer will be this one. This is that or that one. Which one you like? Okay. So that means actually choice of unit cell is arbitrary. In this unit cell, we have drawn the unit cell by choosing chlorine at the corner. In this case, we have chosen drawn the unit cell, choosing sodium at the corner. So choice of unit cell is basically arbitrary. You can draw it keeping sodium at the corner or chlorine at that corner. So that's the one. So now, if you look at the chlorine. So chlorine, obviously chlorine is face center position. If you look at the mid plane here, mid plane over there, you can see sodium, and sodium at the face center position. That means it has two interpenetrating. It consists of two sublattices, and these two sublattices are arranged in face-centered cubic crystal structure. So, if I ask you to explain the crystal structure of sodium chloride, it is actually it often describes two interpenetrating FCC lattices. Okay, and each atom has got 6 nearest neighbor. As you can see, it has got 6 nearest neighbor of opposite kind, like that one. If you look at yourself in this atom, okay, so nearest neighbor is this one and that one, nearest neighbor is that one, and that opposite kind, and also this one and also this one. How many nearest neighbors are there? 6 nearest neighbors are there, okay, of opposite kind. Same status if you choose another like this one, this chlorine, it has got this one, this one, this one, this one, and this one, and then another in the upper unit cell. So it is two interpenetrating FCC. Now materials like sodium chloride itself, and lithium hydride, okay, and then magnesium oxide, manganese oxide, silver bromide, lead sulfide, potassium chloride, potassium bromide have this sort of structure. So if instead of sodium chloride crystal structure, if I ask you to draw potassium bromide crystal structure, it will be the same unit cell. So one of the sublattices will be potassium and another will be bromine. If I ask you to calculate, find out potassium chloride, one is potassium, another is chlorine, and so on. Now, if you look at this one, actually, what is the unit cell dimension? Unit cell dimension is, so if you draw a line, this line, that's the lattice parameter, or that's the lattice parameter. Okay. So along this line, so this is basically A, lattice parameter A. So in A, you have one chlorine radius here, another chlorine radius there. So you have two chlorine radius, and it passed through the diameter of this sodium atom. So we can write A is equal to 2 RCl plus 2 RNA. So that's the relationship between atomic radius and lattice constant in case of sodium chloride like crystal structure. Instead of sodium chloride, if I ask you to write an expression for the lattice parameter for potassium bromide, it will be 2K 2R potassium and then 2R bromine. So okay. Now in previous slides we have calculated packing factor. If I ask you to calculate packing factor for sodium chloride crystal structure, so packing factor is available volume in the crystal. Available volume in the crystal structure is A cube. So A is 2 RCl plus 2 RNA, so A cube. And then in the numerator, it will be, it is face-centered cubic. So that means it has got 4 sodium atom and also 4 fluorine atom. Now the volume occupied by the atom will be 4 multiplied by volume of chlorine atom and 4 plus 4 multiplied by the volume of the sodium atom. Now from the data sheet, we can find out easily that the atomic radius of sodium is this one, 0.097 nanometer, and RCl is 0.187 nanometer. And if we substitute the value of RCl and RNA in this expression, and if we calculate the packing factor, we will see that packing factor will be 0.67. Okay, several moments ago, we have calculated packing factor for FCC crystal, and we have seen that packing factor for FCC crystal is 0.74. Now we are saying sodium chloride is also FCC, but packing factor is 0.67. So obviously, this value is different from ideal FCC crystal structure. Is this an ideal FCC crystal structure? Answer is no, because it has got two sublattices. One is bigger one, another is smaller one. Okay. Now, why this deviation occurs? This deviation occurs because you are arranging smaller atom and larger atom. So in that case, packing will not be so easy due to the mismatch of the atomic radius. This deviation occurs. Okay. Now, if we look at this table, as you can see, as you go down, the lattice parameter increases. Why the lattice parameter increases? If you look at the periodic table, you'll see as you go down, the atomic radius gradually increases. So, if atomic radius increases, lattice constant will also increase. This phenomenon in material science is called Vagard's law. V-E-G-A-R-D, Vagard's law. So, according to Vagard's law, or you see, if atomic radius, in this case, atomic radius and lattice constant is directly related. If atomic radius increases, the value of A will increase, and the unit is in angstrom. So, unit of sodium chloride is 5.63 angstrom, or 0.563 nanometer. Similarly, for the other groups. Okay, and then we're going to study cesium chloride crystal structure. The cesium chloride crystal structure is, if we draw a typical unit cell, it will look like that. So all the chlorine ions are located at the corner, and cesium is at the center. Cesium is at the center. Now, what is the crystal structure of this one? So you will give the answer body center cubic, but this is wrong. You see, this is not BCC. Why this is not BCC? Because the body center atoms are not same as the corner atom. So it would be BCC if the body center atoms and corner atoms are at the same atom. Now this is not body center cubic. So this space lattice is, if you look at the chlorine sublattice, again it has got two sublattices. One is cesium sublattice and other is chlorine sublattice. Obviously, we can see the chlorine sublattice forms simple cubic crystal structure. Now, if we draw the neighboring unit cell, more unit cell here, if you draw the more unit cell over there, okay, and then if you draw another unit cell keeping cesium at the corner, then the body center position atom will be the chlorine. So that means both sublattices form simple cubic crystal structure in this case. Okay. Now, how A and atomic radius are related in this case? This is basically A. So if you draw this line, along this line, no cesium atoms are there. Now, to find out the relationship between atomic radius and lattice constant in cesium chloride crystal structure, we have to draw the largest diagonal, and the largest diagonal is root over 3a. So in this root 3a, if you draw this one or draw any other, so in this line you have one radius from here, one radius from there in root 3a, and the diameter of this is here. So we can write root over 3a, look at here, root over 3a equal to 2 RCS plus 2 RCl. So from here, we can calculate atomic radius. Sorry, we can calculate lattice constant from if atomic radius is given. So as before, if I ask you to find out packing factor in this case, how are you going to calculate? Packing factor is, it will be volume occupied by the spherical atom. So it as before, it is cubic. So it will be A CS CL and then cube will be 1 multiplied by
4/3.
4/3 pi RCS cube plus 1 multiplied by 4/3 pi CL cube. 4/3 pi CL cube. Okay. Now CL is given in this table. Cesium chloride. So it is actually 4.11 angstrom. 4.11 angstrom. Angstrom means 10 to the power 8 minus 8 centimeter. Okay. So CsCl is given, and you know the RCl from the previous slide. RCl is 0.187 nanometer. If you substitute, you know ACS and you know RCl. If you substitute that one, if you substitute this value, then you can calculate RCS from this expression. In this expression, you have three unknown: CsCl, RCS, and RCl. So you know A, the value of A is this, and you know value of RCl. So among these three values, you know two. You can calculate RCS. So RCS will be from this expression. RCS basically RCS will be cesium will be root over 3 A CS CL divided by and then minus 2 RCl divided by 2. That will be that. So it's a simple algebraical relation. From this equation, at first you will derive an expression for RCS. Okay, and then you know A, you know RCl, you will be able to calculate ACS. And then if you substitute the value of all these value of A and then value of RCS, so you will be able to find out packing factor of this one. And you will see the packing factor will be higher than if it is simple cubic. In the previous slide, we have seen that in case of simple cubic, packing factor is 0.52. In this case, you will see the packing factor is higher than that. It will be about 0.68 or 67, like that. It will be much higher than that of the ideal simple cubic crystal structure. Now, why the packing factor of cesium chloride deviates from ideal simple cubic crystal structure? Because this is not an ideal simple cubic crystal structure. It is non-ideal simple cubic crystal structure. Why it is non-ideal? Because in a ideal simple cubic crystal structure, atoms are located only at the corner. There is no atom in the body center position. However, in this case, there is a different atom in the body center position, and due to this body centered atom, its packing factor increases. Okay. Now, if we look at materials, some intermetallic compound like beryllium, copper, aluminum nitrate, copper zinc, copper palladium, silver, magnesium, lithium, mercury, ammonium chloride, thallium bromide, cesium chloride itself, thallium iodide has got this sort of crystal structure. And if you look at this table, If you go down along this, along this column, you can see the lattice constant increases. Why the lattice constant increases? If you look at the periodic table, the atomic radius increases. So if the atomic radius increases, then lattice constant will increases. Lattice constant will increase because of the Vegard's law. Okay, so our next topic is coordination number. So what is coordination number? Coordination number is called nearest neighbor number, which we have studied a little bit previously. Like in case of sodium chloride crystal structure, we have seen there are 6 nearest neighbor atom of opposite kind, and I showed you earlier, if you remember, like this one. If you look at yourself here, so this one, that one, that one, that one, that one, that one are the nearest neighbor. And how many? 6. However, these are opposite kind. So these are nearest neighbor. Now, nearest neighbor number is very important. Nearest neighbor number is very important because the property of the material depends on nearest neighbor number. So that is why study of nearest neighbor number or coordination number is very important in crystallography. The property of the whole material actually depends on nearest neighbor number. Why? If for example, if we consider the resistance of a material, basically tells you that how easy the electron can pass through the material. Now, for example, if you have a large number of nearest neighbor, and if by some means this atom gets more electron, okay, so it will try to disperse that electron in all directions. So if it has got large number of nearest neighbor, it can donate that electron, okay, to all possible way. So the materials having large coordination number, we expect that the resistivity will be less. Okay, so I give a little one example of the how the property depends on nearest neighbor number or coordination number. Okay, so now the definition is, by coordination number, we mean the number of nearest neighbor of an atom has in the unit cell of any crystal system, and it depends on the type of space that is in the crystal system. So like for example, for simple cubic, at first you should find out the nearest neighbor distance. If you locate yourself over here, atoms are located at a distance a, and also atoms are located at a distance root 2a, and also atoms are located at a distance root 3a. So atoms are located at a, and then root 2a, and also root 3a, and also in larger distance, okay, larger distance. But there is no atom located at a distance less than a. So a is the nearest neighbor distance in case of simple cubic crystal structure. Okay. So now you should look, if you look at yourself at any point, you should find out the atoms which are located at a distance a, and that number will be the nearest neighbor. Now let us find out the nearest neighbor number in case of simple cubic. If you look at yourself, this atom, so at a distance a, here is one atom. So this is number 1, and then another atom, number 2, another atom here, number 3, another there, 4, another atom at the lower plane, 5, and another atom will be located in the upper plane. Okay, so altogether the number will be coordination number will be 6 in this case. Coordination number will be 6 in case of simple cubic crystal structure. So coordination number is 6. Now we do the same thing for BCC crystal structure. BCC means body-centered cubic crystal structure. And if you draw a typical unit cell for body-centered cubic crystal structure, this is the typical unit cell. Atoms are located at the corner. Atoms are located at the corner and also in the body-centered position. Now, as before, you should find out the nearest neighbor number. Okay, so if you look at yourself at any corner atom, then atoms are located at a distance here, which is A. Atoms are located at a distance root 2A. Atoms are located at a distance root 3A as well. And also atoms are located at a distance halfway of the root 3A. That means root 3A by 2. Okay, so if we write down here, atoms are located at A, and then root 2A, and then root 3A, and also root 3A by 2. So which one is the nearest neighbor? Nearest neighbor is this one, root 3A by 2 is less than A basically. So nearest neighbor distance is root 3A. Okay, so if we find out, so we should count the number of atoms at a distance root 3A by 2. So if you choose this one as a reference atom, so you can see this atom is the nearest neighbor. Actually, this corner atom is shared by 8 unit cell here, 8 unit cell. 8 unit cell. 4 in its own level. So 1, 2, and then 3, 4. 4 in its own level and 4 in the top level. So each corner atom is shared by 8 unit cells. We have already mentioned this thing earlier as well. So 8 unit cell has got 8 body center atom, and their distance is root 3A by 2 from that corner. So coordination number in this case will be 8. And that is very easy to understand if you choose body centered atom as a reference. If you choose a body centered atom as a reference, this distance is root 3A by 2, this distance is root 3A by 2. This is root 3A by 2, this is root 3A by 2. That one is also root 3A by 2, and that one is root 3A by 2. So there are 8 corner atoms are equidistant from the body center atom. So therefore the coordination number is 8 in case of body centered cubic crystal. Now we will calculate, find out coordination number in case of face-centered cubic crystal. If I ask you to draw a typical unit cell of face-centered cubic crystal, answer is this one. So atoms are located at the corner and also center of the every faces. So if you choose this one as a reference, atoms are located at a distance A, atoms are located at a distance root 2A, and also atoms are located at a distance root 2A by 2, halfway of them. And also atoms are located at a distance root 3A as before. So atoms are located at A, root 2A, root 3A, and also root 2A by 2. So root 2A by 2 is basically less than A. So root 2A by 2 is the nearest neighbor. So how many nearest neighbor of this corner atom has got? So to find out that one,
12.
If we draw the neighboring unit cell, so this one has got one face center atom, and this one has got another face center atom, this one has got another face center atom, and this one has got another. So 4 atoms are at a distance root 2A by 2 in its own plane. Now, if you look at here, and then you will see another 4 atom will be in the bottom plane. That distance is root 2A by 2. Another 4 atom will be the upper plane. Okay, it is very easy to understand. You see, if you consider the room that you are sitting, your own room, as one of the unit cell for face-centered cubic crystal structure. Okay, so if you locate yourself at the center of the room, that means center of the floor. So the 4 corner atoms are at a distance root 2A by 2. This is in your own floor. And if you are sitting in a room in a multi-storied building, okay, so another 4 atoms are lying in the center of the body, center of the 4 wall, center of the 4 walls, and that center of the 4 walls are actually like if we draw this one, another atom will be located over here. So this distance, if you look at yourself here, this distance is a by 2, this distance is also a by 2. And so that distance will be Pythagoras. It will be root 2 a by 2. Similarly for this wall, similarly for this wall, similarly for this wall. Okay, so another 4 atom in the upper one, and 4 atom in the lower plane. Okay, let me tell you again. Draw the unit cell. Of the body cell face center cubic crystal. Atoms are located at the face center position. So from this face centered atom, okay, so put all the corner atoms. You can put all the corner atoms. Okay, so let me look at yourself over here. So this distance is root 2 by 2. 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 So 4 atoms in its own plane. And then the atoms located here is also at a distance root 2 by 2. Why? Because this distance is a by 2 and this distance is also a by 2. So the diagonal distance will be, it is actually a by 2 square Pythagoras, and then a by 2 square and then square root. That will be actually a by root 2 or root 2 a by 2. Or similarly for another atom will be that face. This is a by 2, that one is a by 2, so this is a by 2. Another atom will be here in this phase, a by 2, a by 2, a by 2. So and another atom will be this phase, a by 2, that is a by 2. So 4 atom in its own plane, 4 atom in the lower plane. And similarly, there will be 4 atoms in the upper plane is also. Why? Because there another atom will be here, another will be there. This distance is a by 2, this distance is a by 2, that distance is also a by 2. A by 2, a by 2, and that distance is root 2 a by 2. So all together, so in FCC structure, coordination number is 12, because the nearest neighbor of a face center atom is corner atom. There are 4 such atoms in its own plane, 4 above and 4 below. So all together, the coordination number is 12.